A closed system can exchange energy, as heat or work with its surroundings, while the system itself changes from the initial state to the final state. Meanwhile, some of the state functions of the system also change during this process. Pressure volume work, PV work, is the default thermodynamic work in general chemistry. PV work occurs when the volume of a system changes. Consider a closed system with a piston moving slowly enough for accurate definition of the pressure on the inside of the piston and to the surroundings. The infinitesimal mechanical work to the system, delta W, is equal to the product of the force, F, and the infinitesimal distance the piston traveled, dl. Since force is pressure, P, times area, A, and A times dl is negative of infinitesimal volume change, dV, delta W is equal to minus P dV. Moreover, the total work of a process is the integral of delta W from the initial state to the final state. It is the area under the pressure-volume curve and obviously depends on the path. Therefore, work is a path function. Symbol delta is used for infinitesimal quantity of path function. Symbol d is used for infinitesimal change of state function. There are other types of work beside PV work, such as electric work, but they are not discussed in general chemistry unless otherwise specified. Heat is the energy transfer to a system other than work. Heat is usually caused by a temperature difference between the system and the surroundings. Meanwhile, heat causes temperature change or phase transition in the system, which can be measured. Like work, heat is a path function. Infinitesimal heat is denoted by delta Q. Two systems are said to be in thermal equilibrium if they are linked by a wall permeable only to heat, and they do not exchange heat. The Zeroth law of thermodynamics states that if two thermodynamic systems are both in thermal equilibrium with a third system, then the two systems are in thermal equilibrium with each other. The Zeroth law is important for the mathematical formulation of thermodynamics. It makes the relation of thermal equilibrium between systems an equivalence relation. Like the equality of pressure in mechanical equilibrium, thermal equilibrium is the equality of temperature. In other words, if two systems are in thermal equilibrium, they are at the same temperature, vice versa. For example, ice, liquid water, and water vapor at the triple point are at the same temperature and in thermal equilibrium with one another. Julius Robert von Meyer in 1842 and James Prescott Joule in 1843 independently discovered the mechanical equivalent of heat. In one of experiments, now called the Joule apparatus, a descending weight attached to a string caused a paddle immersed in water to rotate. Joule showed that the gravitational potential energy lost by the weight in descending was proportional to the temperature increase of the water through friction with the paddle. So, a given amount of work could cause temperature change like the same amount of heat. The internal energy of a thermodynamic system is the total energy of all the particles in the system as a state function. It excludes the kinetic energy of motion of the system as a whole and the potential energy of the system as a whole in external fields. The internal energy of a system can be analyzed microscopically in terms of the kinetic energies of microscopic motion of the system's particles from translations, rotations, and vibrations, and of the potential energies associated with chemical bonds and intermolecular forces. In most systems under consideration, especially through thermodynamics, it is impossible to calculate the total internal energy. Thermodynamics concerns changes in the internal energy, not its absolute value. For example, nuclear reactions are not involved in chemistry context. So, nuclear energy does not count as internal energy in chemistry because it does not change in any chemical process. The first law of thermodynamics is a formulation of the law of conservation of energy in the context of thermodynamic processes. It states that the change in internal energy is equal to the sum of the heat and work to the system. A consequence of the law of conservation of energy is that a perpetual motion machine of the first kind cannot exist. That is to say, no system without an external energy supply can deliver an unlimited amount of energy to its surroundings. If the only work is PV work, the thermodynamic work is minus PdV. So, the change in internal energy of the system is delta Q minus PdV. For example, the volume of a system at constant pressure, 1 bar, increases by 1 liter, while the system receives heat of 150 joules. The internal energy of the system increases by 50 joules.